Hello. Yeah, all of you can listen.
Yes, sir.
Yes, sir.
Okay. So anyways, we understand this algorithm of deep Q learning, and soon maybe in our next lecture or next to next, Daksh may be covering the code part. Okay. Deep Q learning we understand in detail. Now, so as we have said that we have an environment, given such an environment, agent is going to play. So basically it has to play in such a way so as to learn an optimal behavior.
So I mean in policy iteration. So if we look the sun physically problem, then we can say that it will converge. Is there any mathematical proof of this?
Because policy iteration there is a DP. So they have shown that DP, and if you keep on iterating over the policy, definitely it's going to converge, because DP ensures that after every iteration policy got improved. And it's assumed that there is some optimal solution of your problem. If there is no optimal solution, we don't know, but most of the problems we define in such a way so that they are having a solution. So if you have a solution which is having an optimal, if you have a problem which is having an optimal solution, and DP is going to get the thing marginally improved every iteration, so eventually it will reach up to that. But the point is that when, how fast, and so on. So that's why we discard policy iteration, because we cannot use it for this, but we utilize that idea of optimal solution and enforce Bellman optimality over our predictions. You cannot predict anything arbitrarily. If it is optimal, then Bellman optimality need to be enforced over that, right? So that is what deep Q learning is doing. So essentially deep Q learning is not trying to solve the recurrence DP, because that may be huge amount of time and so on. So we actually said that you predict, but don't predict, enforce the Bellman optimality, right? True. Now, so anyways, as we have reiterated, so that was the work that's being done by deep Q learning. Now somebody comes and say that, sir, essentially what you want from me, you want a policy. So today you require pen, pencils and all, right? So please have your pen, pencil ready. You will have to write certain things. All of you, those who are attending, copy and pen will be required. Some mathematical stuff is about to come, right? So first point is, now somebody will say that, sir, what you want? You want a policy. In deep Q learning, what is your policy? That's a greedy policy. You are learning Q function using greedy policy and then playing the game. That's what which is happening. Then somebody will say that, sir, your policy is greedy. Okay. So essentially you are trying to learn the best optimal Q function. Okay. Now other point is that we have a network which is giving you the Q function. Can I directly learn the policy? In fact, you are also trying to get the best Q function and your policy is fixed. But essentially your system is working in this way. Can you directly give me the policy? Because essentially what you want something by which you can decide what to do at this state. And that is your policy. Policy is like Ram Krishna Paramhans. That is the thing that you want. You just go and to this guy say that, sir, IT1D, बताओ क्या उसने कहा MIT उसने कहा Harvard दिए, whatever path that you wanted to choose. But you want, I'm telling you the state, you tell me the action. And essentially that is your policy. How you have done that? You have done it using Q function. Q function can tell you that at this state, if you take this action, what is the maximum reward that you can get. So Ramkishan Paramhans actually knows that at this state, if you take this action, this much, this action, this much, this action, this much, this action, this much, and out of that you take the greedy policy. Whatever the maximum you take it. Now I am saying that directly can we learn the pi? So pi can. So now we are talking about a network which can actually be seen as a set of parameters theta. So previously your theta was Q function. Theta was like, I forget your name. So Balkar is a theta, U was Balkar, U was theta, and U was just your Q function. Now I am saying that no. Wait, तुम्हारा नाम मैं भूल गया. Komal. So now Komal is the policy. Previously he was just a simple manager. You tell me, you tell me, you tell me, you tell me. Maximum come in. Now he has to be. Now he is not going to get that. You tell. Now he has to tell directly. अभी इसको बलकार नहीं मिल रहा. Can I do that? Because previously I was training you. Now I'm training him directly. Balkar bhag gaya. Yeah, I wanted to train it in a different way without utilizing Balkar because I only want this guy. So just give me that part. So now in that theta space, suppose that theta is a 50-dimensional space. Now forget about that 50. You cannot visualize. Suppose that theta is a 3-dimensional space. This is one point. What is this? This is Q function. If it is deep Q learning, I can say that with these 3 parameters, this can actually be a policy. Now this is one policy. This can be second policy. This can be third policy. How good or bad we will talk about. But this is my parameterized space. If it is 3D, this is like this. This is my policy number 1, policy 2, policy 3, policy 4. Infinite policies are there. Now just think about, we have a 50,000 dimensional space. We cannot think, but you just assume. And in that, if you choose a point, that's a policy. 50,000 parameters are there, maybe in your network. One point, that's one policy. Second point, second policy. And out of all these policies, you want the best one. Now we need to define what is best. So previously we were trying to train a network which can optimize to maximize my DCFRs by enforcing Bellman optimality. Understand? That's an important thing. I was just only enforcing Bellman optimality. True? No issues. Tick. Now, again, I am moving in the some space where one point is actually a policy, and out of that, if I somehow know this policy is better than that policy, then basically I want to know what is the best policy. And what is the best policy? Yes? No, greedy is the policy that you are using when you have Q function. And if you got the best Q function, then you ask SPA, SPB, SPC, SPD, and then you take the max. That's the best Q function when you got best Q value, right? So that is the previous thing, Q learning. Now forget about Q learning. I'm not touching Q function. We do not want Q function. Why you are doing the Q function? Acha, example. I got a very good example. So you are walking in the forest and you have got a lion chasing you. Now you have 4 actions. You can stay and fight. You can climb this. You can do this. You can do that, and 5 actions. So what a person is going to do? Either is he going to apply, that with this is the Q function, that's the Q function, this is this, or that is this. I mean, I have got this example from the book. He is saying that no, we don't do that. We just apply the policy. That is fast. Several times it is not even quantifiable that this action is better than that action. And you do not actually want. Understood? I mean, take this example, line is coming, you are going to be, tree was very near to you and you wanted to rise up onto that and then wait for there. But now you'll have to wait and then night happen and so on. So you cannot compute all those things because several times RL problems are very, they want answer fast, at least the predictions when you're doing the inference, it has to be fast. So if I have a Q function, I have 10 actions, then 10 times you have to apply, then get the value. If you have a pi, it will directly tell you the action. Just you take and go. Several times it is good because you need not to quantify each and everything. You cannot quantify. You may say, yeah, this is good. You cannot tell why. How much this is better than others. That is why we started to talk about the alternative approach. I'm not saying that this is better or that is better right now. We'll talk about that. But this is an alternative approach in which we are directly parameterizing policy. So previously your Q function was being parameterized by theta. Now your policy is going to be parameterized by theta. Clear? Okay. So instead of using DN and approximate Q function, I talked about, now this is the new word for you, in which your pi is nothing like a greedy policy, but it's actually parameterized by theta. We keep on writing it that theta is coming from some R, it's some dimensional vector or m dimensional vector. Pi theta is the parameterized policy. Clear? Now, what is j theta? J theta is the value of that pi, because pi is my theta. J theta is the value of this pi. It's nothing but the expected value of the DCFR. What is the meaning of this? Let me tell you. This is the DCFR. This is DCFR following pi theta. So given pi theta, you are following my pi theta. Pi theta is my network. You give something, it's going to give you an action. Pi theta may be your father, maybe your friend. Suppose that Balkar's pi theta is this. What's your name? Chinmay. Chinmay. Balkar kuch bhi karega, Chinmay se pooch ke karega. How can you estimate how good Chinmay as a pi is? You follow him for 50 days, 10 days, 20 days, and then estimate your returns and then take the expected value or the average value. That is going to tell you how good or bad he is. And if you somehow can differentiate it, you can change him. Because if you wanted to change, you remember that theta, if you can differentiate, then you can change it to the new thing using the stochastic gradient descent. Theta is equal to theta minus theta times theta del L by del theta and so on. This is okay. Please write it down. This is important. J theta expected DCFRs given pi theta. Simple enough. Jaldi jaldi likhte jana. Okay. So that's the thing pretty much that we want. What do you want? What's your goal? What is your goal? My goal is very simple. Arc max over all thetas, j theta, theta at stake. So don't worry, बलकार अगर कुछ छूट जाए, यहाँ ध्यान देते रहो. मैं लिखवा क्यों रहा हूँ? Let me tell you, because ना जो कुछ भी मैं बोल रहा हूँ उसको लिखते रहो. ठीक है, कान ओपन रखो, लिखते रहो. 100% समझ में आ जाएगा. बहुत सारा है अभी इसमें. ठीक है, जहां भी मिस करे गायब हो जाओगे. This is actually our second algorithm. First is deep Q learning. This is reinforced algorithm that we are going to see. You want to say anything?
Yes, sir. I'm a little bit confused with you. I mean, previously we were computing
Q function.
And now we are computing j theta.
No, now we are computing. Now we are. You can say that now we are approximating pi. Previously you are approximating Q.
So the right hand side of j theta comes from
Oh no, but here you can have better parameters. There we cannot, now I'm going to show you that how we have got the loss function of this thing. But my first motivation is that Q function, you don't know how to optimize a Q function, but that's an optimal function. So it has to follow the optimality. So I said that your answers need to be optimal. So I have to enforce Bellman optimality.
It may happen that if we take some certain action, then we will end up with some more gross state.
That's true. That is true. But this is expected value, na? So it may happen that you take something and then end up in some poor situation. So those on those states, those actions probabilities are minimized. Right? That is what you want. That will be happening even in this, even in the case of Bellman, because that will not follow the Bellman optimality. Right? And if it's not following the Bellman optimality, your answer and the Bellman optimality answer will be very far. So in the case of Q learning, when you minimize that, every time you need to be optimal. If you are optimal, all of your decisions has to be optimal. So in that way, we have managed over there. Here, what we are going to do is that at those states where you are performing very bad, those probabilities need to be. So that will happen in between, you will see. But before that, again, if I say that, remember what is pi? अपनी copy में लिख लो वरना भूल जाओगे. What is pi? Pi is a given s, है ना? A given s. I give you a state, you are going to give me the action. The probability by which at this state this action has to be chosen. Okay. Pi can be stochastic, pi can be deterministic. Deterministic, like you give me S, I am directly giving you A. ये action लो, इसकी highest probability. Probabilistic, you give me S, I am not going to give you an action, I am going to give you a vector. That's a probability distribution. That this probability, this action with this probability, this action with this probability, this action with this probability, and so on. And out of that, either you choose the maximum or you randomly choose from that probability distribution. You can use epsilon greedy, always follow. Epsilon greedy, with very high probability, you choose the maximum. With low probability, you choose the others to explore. Now, ये सारी चीजें anyways, they are there. They will be there. This is true that you want J theta. You want that theta out of all possible thetas, which will maximize this guy. That theta is your answer. Clear? Formulation, simple, straightforward. And by the way, that's your reinforced algorithm. How to design such an algorithm? So first, let us talk about a trajectory. And we all know that what's a trajectory. I have a network. To utilize that, I am having you, Komal. Komal ko as bataoge, it's going to tell you an A. Komal ko leke you can play a game. That is one trajectory. Good, bad, we are going to see that. But you can play with Komal, you can play 500 games, 1000 games, 50,000 games. And then you can assess how good this policy or bad this policy is. Okay. That's the trajectory. Definition of a single trajectory. What is a single trajectory? Tau is equal to S0, A0, R0. Clear? S state, A0 action, R0. Please take the phone and बाहर ले जाना उसको. Tau S0, A0, R0, S1, A1, R1, S2, A2, R3, and then at some point you got terminated. This is your single tau. Clear? No issues. If I have game, you choose a pipe, Komal.
Sir,
Yes,
yeah,
Aryavad.
yeah, voice is coming now, sir.
Why is coming now? Okay. So game initial state, then we have so if I have a pie, I can play multiple episodes of a game, some initial state, and then this is trajectory number one, and the reward, that total reward that I get, that is R tau 1. Then you can get R tau 2, then R tau 3, then R tau 4, and so on. So how good this pie is? How good this pie is? Dipali Singh, can you tell how good this pie is?
Sir, I don't know.
No, so don't worry. Point is that for first trajectory, you have got R tau 1. Is this even okay, or you don't understand that for first trajectory, R tau 1?
Yeah, that is okay.
That's okay, because you are having some pi. You started to play with that pi with this initial state, then this, then this, then this, then this, and then this. And you have got R0, R1, R2, R3, R4, R5, R6, R7, R8, and add all of them. That is R tau.
Yes, sir.
But that's a discounted DCF. That's not DCFR. So that's a simple average, a simple addition. But you can do with discounted and DCFR. If you do that, what will be that? Okay. So if this is R0, from here, if you have got R0, then you can compute that at this point, what is the reward, at this point, what is the reward, at this point, what is the reward, at this point, at this point, at this point. You can compute the discounted DCFR, and then this is R tau. This is the second trajectory, this is third, and this is fourth. If I say that I am fixing my pi, given this pi, I have got these trajectories, then with respect to this, what is your total performance of your pi? It can be addition of all of them. Deepali, yes, no?
Yeah, yes, yes.
It
sir.
can be the addition of this, but do you think that with the same probability all of them are occurring? No,
No.
because this will be the probability, this will be the probability, this is the other probability, this is the given theta. I am fixing my theta for one point. At this point, my theta is fixed, my pi is fixed. Given a fixed pi, which means that my theta is fixed, you have got this trajectory with some probability. If all the probabilities are same, then it will be addition. Else, this multiplied by this multiplied by this multiplied by this, and this multiplied by this. That's the expectation of the reward over all possible trajectories. Not only 4, you have to take infinite.
On this, like different taus depend upon the initial state. If it is determined state,
Tau will be,
like you're saying, the probability for tau 1.
probability for tau 1 is, yes, bolo bolo.
So like tau 1 अंकर हो रहा है जब एक particular initial state है.
हाँ,
And tau 2 हो रहा है जब different initial.
नहीं, ऐसा तुमने सोच लिया एक पॉइंट के हिसाब से, ऐसा नहीं है, because epsilon greedy approach लग रहा है ना. Even if I give you the same pi, same initial state, it's keep on changing, because with 95% probability you choose the action, 5% you discard the action. No, the point is that epsilon greedy is that 95% I will choose the answer, 5% I will discard that. That is epsilon greedy. Epsilon means that with a very small probability I am choosing something else I am greedy. I'll choose with 95% high probability, with a very high probability what you are suggesting. So it may be this, but as we have said that it has to be this, it can actually be seen as this. Okay.
Sir, is it similar to GMM?
GMM. So in the case of GMM, what happen is that you have multiple modes, mode 1, mode 2, mode 3, and so on, and you give each of them some mu, some probability.
You are giving the probability.
But that is anyways for any random process. So if I have a random process, this is the random process which is happening. These trajectories are being chosen randomly following a pi. So they are going to have different probabilities. So this is nothing but the expectation. There's a formula of expectation, by the way. You can see that this is the reward, and with this probability you are going to get this reward. This is the reward. With this probability you are going to get. So for I equal to 1, basically for first trajectory, with this probability that trajectory will be selected, and with this probability that's the reward that you are going to get. So you multiply. There's a basic formula or a definition of the expectation or the average value that we use to compute. Okay, now so this is the expected reward. This is your expected reward. What does that mean? That means that if your theta is fixed, there is a distribution pi given theta tau. If I fix my theta over pi's, I am going to have a distribution. Out of that, we choose any tau and average it out. That's the expected reward for that theta, which is equivalent to a tau, which is equivalent to pi. For a given pi, this is the expected value. जैसे कि मैंने बोला बलकार ने चिन्मय को बना लिया अपना pi. So Balkar keep on playing so many things. 50 days after, what is this expectation? This is over 50 days for Chinmay. He keep on adding. If you देखा Chinmay say this much amount I got, and no, I have to change Chinmay, or he is good or bad, whatever, depending upon this value.
Why are we saying expectation? Because we have already like played for 3 days.
Yeah, so this expectation is the average value. The definition of expectation. So I assume that probability course people have done, but random process you not have done. Understand, if there is a random process, let me give you a 2 minutes introduction of a random process. Random process, everything is happening with a probability. So if I say, hey, you are a function, can you, if I give you this value, can you tell me what's your answer? You will say no, I cannot tell you a single answer because I am a stochastic process. It's a probabilistic process. It is not deterministic. अरे x स्क्वायर हो तुमको मैंने x स्क्वायर एक गेंद दूंगा 2, तुम मुझे क्या बोलोगे? हमेशा कभी बदलेगा? जैसे डिटरमिनिस्टिक प्रोसेस. रैंडम प्रोसेसेस में ऐसा नहीं होगा. मैं तुम्हें 2 दूंगा, कभी तुम 3 बोलोगे, कभी तुम 5 बोलोगे, कभी तुम 7 बोलोगे, डिपेंडिंग अपॉन डिफरेंट प्रोबेबिलिटीज what is happening inside this function. So you cannot directly see a random process. How can you see that a process? Random process can be seen only via random variable. Or random variable is actually a function, probability density function. So random variable is going to have a function. Random variable is saying that, hey, random variable x equal to 5 is saying, hey, x equal to 5, with this probability I am this. With this probability I am this. With this probability I am this. So basically, when I say you are an x, सिक्का उछाला, क्या आएगा? अरे डाइस, क्या आएगा? पता नहीं. 1/6 this, 1/6 this, 1/6 this. Now, what is your outcome? What is the expected value of your outcome? 1/6 into 1 plus 1/6 into 2 plus 1/6 into 3. What is the expected value? Okay, let me give you. You understood this example, na? So if I say that there stocks, in this stock, if you invest, this much amount of return, this much amount of return, this much amount of return. But you choose this stock with the probability this, with this probability you will choose this, with this probability you will choose this. And you keep on playing every day with the same probabilities, you are going to get different amount of stocks. Even with the same probability, same reward, you are going to get different outputs every day, because expectation is same. Sorry, your probability is same. So you are going to sometimes choose this, sometimes you choose that more, sometimes you choose something else. but what is the on an average how much amount of money that you are going to get. So that's the definition, that this multiplied by the probability. What is the output of your dice? What is the probability of that? What is the output of your dice? What is the probability of that? So if somebody will say that sikka uchala, what is the expected value that you are going to get? That's 0.5. Even though it's not there, 0 or 1, expected value is 0.5, because 50% this, 50% that, 50% 0, 50% 1, 50 multiplied by 1 divided by 100, that is 0.5. If it's not a biased point, if it's a biased point, 0.7 times 1, 0.2 times 0, then 0.75 multiplied by 1. Why we integrate? We integrate because it's a continuous function. If it's a discrete summation, and do it for all taus, do it for all possible outcomes. If it is 0, 1, it will be 0, then it will be 1. If it is summation 0 or 1, if it is dice, it will be 1, 2, 3, 4, 5, 6. Yeah. So right now it's a continuous, saying integrate. Okay. We understood that theta asterisk is going to be equal to the argmax of our j theta, but our j theta is essentially this thing. Okay. By the way, this is so j theta is now not a minimization function, but it's actually a maximization function. So it can actually be said as a not a loss function, but a gain function. Forward pass, you require the loss or the gain. If it's a gain, then you will differentiate. I mean, then you maximize it. How can you maximize a term? With a minimizing framework. If you have a minimization framework, how can you maximize something?
Right. I mean, we can reciprocate.
But reciprocate make things very small. So we just minus it up.
Yes.
Negative value and then minimize.
In probability, we generally do like this.
But in the case of probability, because in the case of probability, if it is say 0.5, 10 power minus 6. So 1 divided by 10 power minus 6 will be a very big number. So that's why हमें वो minus. So usually हम लोग minus लगा के utilize the same framework. Anyways, it is going to be minimized. Whatever you write in your code, everything will be minimized. But you just check that they will take j theta and take the minus of that to minimize. Now that's your loss. In fact, that's your gain. This is your derivative of that. R tau is not dependent upon theta, because that is the property of your invariant. So that is why you can see things over here. This is actually the gradient of an expectation, because anyways this is right, j theta delta theta j theta, right? So this is the gradient of an expectation. Now gradient of an expectation nikalna, it's difficult. Why? Because you cannot get the exact average value. Why? How many games you play? 50. Do you think that that's the correct average? You play 100 times. And even though it's not a sikka, which is not having any biases, your policy is having so many different types of biases. So if I say gradient of expectation, which essentially means that you need to get the expectation right. How can you get that expectation right? You have to have huge amount of samples. How many? Essentially infinite amount of samples. So this is an intractable thing, but slight amount of twist which is going to happen, and you all know a small trick. This is the thing that we are interested. Understand what is this? That's the probability of tau given theta. क्या मतलब है? अगर ये theta, if this is my, if I give you my pi, with what probability this tau is going to be selected? है ना? यही तो है ना? उसका डेरिवेटिव निकालना. ऊपर नीचे आई जस्ट मल्टीप्लाइड, सेम थिंग, दिस एंड दिस.
Sir, previously you said tau is independent of theta.
Who? Probability.
Tau.
Tau is going to be determined by theta, na, because you are theta. So depending upon you, you will be telling that इधर जाओ, फिर इधर जाओ, फिर इधर जाओ, फिर इधर जाओ. ये एक trajectory बन गया. So that is being governed by theta.
Pi.
R was
That's a pi, ना.
Okay, yeah.
R वो दूसरी चीज था. ये देखो उसने दिमाग लगा लिया कॉन्टेक्स्ट से कि मैंने क्या बोला था, इसने क्या एज्यूम किया. ठीक है, ये मल्टीप्लाई हो गया, ये मल्टीप्लाई हो गया, सिंपल है. कौन आदमी ये वाली बात समझ रहा है?
It's a simple integration.
हाँ, तो हमने यहाँ पे किया क्या?
We have differentiated.
हाँ, तो इसका डिफरेंशियल ले लो, इसको पता होगा ये मैथ का है, ये डिफरेंशियल है. हाँ, ये ले लो, इसका डिफरेंशियल करोगे तो लॉग है तो 1 बाई दिस थिंग हो जाएगा, तो 1 बाई दिस थिंग और डेरिवेटिव ऑफ दिस वही तो रखा है ऊपर, तो इस चीज को ऐसे लिख दिया. यस नो, यस नो, यस नो, बहुत ही सिंपल है ना. यस यस. तो इस चीज की जगह प्रीवियस इक्वेशन में ये चीज रख देता हूं. पता नहीं उन लोग को सुनाई दे रहा है, सुनाई दे रहा. ओके, this is the expectation of gradient. Previously the gradient of expectation, now it's a grade expectation of gradient. Now why it is useful? Because now you take gradient 1, then you may take second number of gradient, then you take the third number of gradient, and then you do the averaging.
Expectation is also, I mean, linear.
Expectation is also needed, so keep on adding. तो जितना ज्यादा सैंपल ले लोगे उतना अच्छा आएगा. ठीक है, जितना कम लोगे उतना खराब आएगा. बट अगर ये उल्टा होता, then expectation need to be computed a priori, so you cannot compute that because it's an impractical thing. But anyways, this trick is not just because of this, but because you will soon understand that why we are doing this. But basically that's the delta theta, that's the gradient of my j theta. यहाँ किसी को कोई भी इशू है? No issues, no issues. Anyways, I've said that कि क्या है इशू, कि कितना ट्रेजेक्टरी खिलाओगे, क्या करोगे, एक्सपेक्टेशन कैसे निकालोगे, रिवॉर्ड्स का सारी ट्रेजेक्टरी के ऊपर कंप्यूट होना चाहिए. बेसिकली नाउ फॉर सम ट्रेजेक्टरी टाउ 1 एक ट्रेजेक्टरी पकड़ रहा हूं अभी तुम्हारे लिए, अभी अभी टाउ 1 ऐसे होगी कुछ S0 A0 R1 A0 A2 R2 एंड लंबी सी ट्रेजेक्टरी. Let us compute the probability of tau 1 given this. मान लो कि ये है तुम्हारे पास, मतलब मैंने तुम्हें थीटा दे दिया. थीटा क्या है? मेरा थीटा नेटवर्क है. तुम डिजाइन करोगे, बन जाएगा, पास करोगे, आउटपुट आ जाएगा. मान लो ये दे दिया. With respect to this, can you actually compute what is tau 1? What is the probability of tau 1? अंदर जाते हैं थोड़ा, बहुत ही सरल है, अंदर जाते हैं. S0 पे A0 लेने पे मैं S1 पे पहुंचा. व्हाट इज दिस? दिस इज ट्रांजिशन प्रोबेबिलिटी. ये तुम्हें नहीं निकालनी है, कौन बताएगा? एनवायरनमेंट एमडीपी में डिफाइंड होगा. S0 पे A0 लेने पे S1 पे पहुंचे with what probability? This. But S0 पे A0 लो, ये किसने कहा? फाइन. जब ये दोनों चीजें होंगी तब आप S0 पे A0 को लेकर के, क्योंकि कौन कह रहा है S0 पे A0 लो, ये कह रहा है, और S0 से A0 लेने पे मैं इस स्टेट पे पहुंचूंगा, ये कौन कह रहा है? S1. दैट इज एसेंशियली S0 A0 R0 के बाद S1 मल्टीप्लाई कर दिया. Same thing, S2 S1 A1 pi theta, theta is same because अभी तो नेटवर्क एक है और ये एक ही ट्रेजेक्टरी चल रही है, बार बार तुम कोमल से ही पूछते हो S1 A1 and so on so on so on so on, so मल्टीप्लाई कर जब तक कि टर्मिनेट ना हो जाए. These are your transition probabilities, these are your parameterized policy से जो आउटपुट आ रहा है. इसमें कोई प्रॉब्लम दिखती है? अगर मैं कह दूं ये कंप्यूट करो तो तुम किसी भी गेम के लिए कंप्यूट कर सकते हो, लेकिन कब नहीं कंप्यूट कर सकते? इससे तो इसमें तुमसे एक बड़ी अजीब सी मांग कर दी, ट्रांजिशन प्रोबेबिलिटी. सिंपल गेम्स के लिए ट्रांजिशन प्रोबेबिलिटी भले तुम बता लो, कॉम्प्लेक्स गेम तो दिस नीड्स द मॉडल. दैट इज व्हाई if you utilize T, any algorithm utilize T, that's a model full algorithm. It actually requires the MDP, but there are problems that cannot be properly, you can formalize but you cannot compute the full T. Cannot compute the full T. There are infinite amount of states, continuous states, and huge amount of actions for every state, every action. Kahan se nikaloge? Forget. This is the problem that this is actually because your j theta and the derivative of that, both of them, so your j theta is actually requiring this. Why? Because this being multiplied by the amount of reward that you are going to get when you select this tau 1, this multiplied by r tau 1, but this requires in turn this, but you cannot use this. So that's the problem where we got stuck. Clear, 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 clear. Okay. Just once more, two things I need to show you again. That what is my j theta? This is my j theta. What is the derivative of my j theta, which is not this? Derivative is this. This thing and the log of this. Previously we have this thing and I guess this multiplied by this. Now it's the log of this. Just summarizing, p tau theta, p tau given theta is nothing but pi. But let us say summation and pi is complete multiplication. This thing, there's a transition probability multiplied by the policy decision. No issues because there's just a summarization. Previously I've written in this whole thing multiplication, now it's under this pi. Same thing, you require T. We have shown this. We have shown this. Pi multiplied. So basically, that's a pi of transition probability multiplied by the pi, right? Which is this thing internal. If I take a log of that, why I'm doing the log? Because when you do backward propagation, you do not require j theta. What was j theta? R tau multiplied by p tau given theta. P tau given theta is problematic. P tau given theta is problematic for you. Understood? Why? Because it required T. I just have shown. Let us take the log of that.
We are taking log of that because of log is multinomial integration process. And the probability of probability can be written in the summation form.
Both of these things are true. Both of these things are true.
It is joint can be also.
But that's not the only reason why we have done that. By the way, what we have said, that's true, because if I give you huge amount of very big multiplication, you are out. You cannot do anything. Multiplication, lamba sa, डिफरेंशिएट कर ही नहीं पाओगे, बर्बाद हो जाओगे। यस, लॉग लगाओ तब करो मल्टीप्लाई। ये देखो ये इंटरनल फंडे हैं, आपको पता है। चश्मा लगा लो लॉग का, मल्टीप्लिकेशन दूर से ही तुम्हें समेशन होता दिखेगा, समेशन पे डिफरेंशिएट कर ले जाओगे। तो ये तो क्लियर है, मल्टीप्लिकेशन दिखा नहीं लंबा, लॉग लगा के आगे काम सारी दुनिया करती है। इट्स फर्स्ट थिंग। मोनोटोनिकली यस, बिकॉज लॉग इंटीग्रिटी नहीं चेंज होने देता कि मतलब मैं मैक्सिमाइज इसको करूं कि इसको करूं, अरे लॉग लगा के भी मैक्सिमाइज कर लो, कोई फर्क नहीं। तो मोनोटोनिकली इंक्रीजिंग फंक्शन है। इट इज जस्ट लाइक कि मैंने एक्स स्क्वायर को करना है कि लॉग एक्स स्क्वायर को करना है, जैसे 2 log x। बिहेवियर सेम रहना चाहिए, ठीक, दोनों बात है। लेकिन ये दोनों ही सिर्फ जवाब नहीं है, आधा आंसर है। बिकॉज ऐसा गंदा सा मल्टीप्लिकेशन तो कभी नहीं करोगे, पार्शियल डेरिवेटिव, ये डेरिवेटिव प्रोडक्ट रूल एंड ऑल, पर कॉम्प्लेक्स हो जाएगा। सबसे पहले लगाया लॉग। लॉग लगाने से ना तुम इनको देखना अब पसंद करोगे। अगर मैं डिफरेंशिएट करने को बोलूं तो सबसे पहले लॉग लगा के अगर मैं ये दिखाऊंगा तो तुम कहोगे अच्छा सर कर लेंगे। तो लॉग ऑफ दिस, अभी समझ में आ रहा होगा कि वहां हमने लॉग के साथ वो मल्टीप्लिकेशन डिवीजन जो किया था वो ट्रिक लगाई क्यों थी। वो ट्रिक इसलिए लगाई थी कि अब तुम इसको लॉग के अंदर डाल सको, ये चीजें लॉग में आ गई। देखो ये भी लॉग में गई, ये भी लॉग में, ये समेशन बन गया। एक इसमें बड़ी अच्छी चीज है कि इसका डेरिवेटिव किसकी टर्म्स में निकालोगे, थीटा की टर्म्स में। थीटा की टर्म्स में थीटा इस पर डिपेंड ही नहीं करता है, ये 0 हो जाएगा, खत्म। नाउ अंडरस्टैंड, जे थीटा मांग करता है इसकी, न कि लॉग की। लेकिन जे थीटा की जरूरत ही नहीं है, क्योंकि बैक प्रोपेगेट तो डेरिवेटिव किया जाता है और डेरिवेटिव को ये चाहिए नहीं, तो ये मॉडल फ्री हो गया। बात है समझ में, दो स्टेप है सिंपल, इसीलिए हमने ऊपर नीचे डिवाइड किया। एंड ये चीज हो गई 0 इंडिपेंडेंट ऑफ थीटा, सिर्फ ये बचा। Therefore, gradient of this guy is actually equal to the summation of gradient of this guy। ये क्या है, ये क्या है, ये मॉडल है, ये मॉडल का आउटपुट है। एक मॉडल बनाओगे डीप लर्निंग का, उसको एसटी दोगे वो 80 बताएगा, एसटी दोगे 80 बताएगा, एसटी दोगे 80 बताएगा, जैसे जैसे बताता जाए, चलते जाओ चलते जाओ चलते जाओ चलते जाओ, ट्रेजेक्टरी बन जाएगा। ट्रेजेक्टरी बन, यही तो है वो ट्रेजेक्टरी जिसकी की बात हो रही है। उस ट्रेजेक्टरी की प्रोबेबिलिटी क्या है, हमने कहा उसका लॉग ले लो। पहले इसी पे काम करते थे, लॉग लगा लोगे, मोनोटोनिक मोनोटोनिक वाला है तो वो सेम ही टाइप की वैल्यूज आएंगी, और उसका डेरिवेटिव निकालो। एंड डू इट फॉर t इक्वल टू 1, t इक्वल टू 2, t इक्वल टू 3, t इक्वल टू 4, t इक्वल टू 5। मतलब ये कि मैंने अपने मॉडल से पूछा, पहला स्टेप लो, पहला स्टेप लिया ग्रेडियंट निकाल लिया, दूसरा स्टेप लिया ग्रेडियंट निकाल लिया, तीसरा स्टेप लिया ग्रेडियंट निकाल लिया, चौथा स्टेप लिया ग्रेडियंट निकाल लिया, सबको ऐड कर दिया। ये है वो। अभी मैं फाइनली और फिर से बताऊंगा कि एल्गो एक्चुअली में कैसे काम करती है, लेकिन थ्योरी ये समझ लो कि क्यों। ये सब बातें बता दी मैंने। Therefore your delta j theta, that's the gradient of your j theta। j theta का ग्रेडियंट क्या हुआ, ये याद करो, यहाँ पे क्या था और अब यहाँ पे ये आ गया। पहले यहाँ पे p टाउ वो सब रखा था, ये लॉग का ही आ गया। ये बड़ा अच्छा है क्योंकि ये क्या, ये लॉग लाइक्लीहुड है, ये लाइक्लीहुड है, ये लॉग लाइक्लीहुड है, उसका डेरिवेटिव है, उसका एडिशन है, और उसमें हमने r टाउ मल्टीप्लाई किया। मतलब ये कि ये इस स्टेट से यहां गया, फिर यहां गया, फिर यहां गया, फिर यहां गया, फिर यहां टर्मिनेट हो गया। दिस इज t इक्वल टू 0, then 1, then 2, then 3, then 4, then 5। यहां से यहां आया, S3 पे A0 लिया, S1 पे A1 लिया। किस किस प्रोबेबिलिटी से लिया ये बता रहा है, नेटवर्क बता रहा है, उसका लॉग लेते जाओ। और ये जो काम है उसका लॉग लेते जाओ, लॉग लेते जाओ, लॉग लेते जाओ, लॉग लेते जाओ, जोड़ लो पूरा, और उसका डेरिवेटिव निकाल लो। नेटवर्क में बिल्कुल ऐसे ही होते, प्रोग्राम में दिखेगा भी आपको। और उसके बाद यहां पे टोटल कितना पाते वो मल्टीप्लाई कर दो। ये अप्रोक्सीमेशन है, आपको दिख गया ना, बिल्कुल सिंपल सा अप्रोक्सीमेशन जो मैंने शुरू में भी दिखाया था आपको। R1 R2 R3 मतलब रिवॉर्ड 1 रिवॉर्ड 2 रिवॉर्ड 3 रिवॉर्ड 4 रिवॉर्ड 5, फाइनल रिवॉर्ड ये आ गया R टाउ। तुमने कहा R टाउ में P प्रोबेबिलिटी गिवन सच थीटा, इस टाउ के चुने जाने की प्रोबेबिलिटी मल्टीप्लाई कर दो, नहीं निकाल सकते। हमने कहा डेरिवेटिव ऐसे निकाल लो। क्या है? स्टेप बाय स्टेप 1 2 3 4 मल्टीप्लाई करते जाओ और फाइनली इसमें मल्टीप्लाई करके जोड़ दो। दैट्स योर रीइंफोर्स एल्गोरिथम। दैट्स योर सेकंड एल्गोरिथम। हमने पहले डीप क्यू लर्निंग सीखी। दिस इज योर रीइंफोर्स एल्गोरिथम। क्लियर है सबको? अब ये दोनों के कोड ऐसे, इसके बाद यहाँ पे बहुत से पंगे होंगे इसको लेके, ठीक है? वो क्या पंगे हैं मैं अभी बता दे रहा हूं, बस 2 मिनट में हम लोग खत्म कर रहे हैं। लेकिन उसके स्टेप्स आगे आगे करके मॉडिफिकेशंस आएंगे। पहला पंगा क्या है? इस पूरे को या तो अवार्ड मिलेगा या तो पनिशमेंट मिलेगा। भाई मतलब या तो तुम जीतोगे तो हारोगे, तो या तो अवार्ड मिलेगा तो नहीं तो पनिशमेंट मिलेगा। तो ये सारे लोग बकवास हैं। मतलब सारे एक्शंस के, सारे स्टेट के करस्पॉन्डिंग एक्शंस या तो इकट्ठे अच्छे साबित होंगे या इकट्ठे खराब साबित होंगे। क्या ये सही बात है? लेकिन वो फिर भी मर गए क्योंकि अंतिम में तुमने यहां पर एक गलत चाल चल दी। क्या करो, कर दी तो कर दी, तो ये हार गया। लेकिन यहां पे तो जबरदस्त खेले थे तुम। जब आप यहां पे जबरदस्त खेले तो कौन इसको अकाउंट करेगा? दिस इज कॉल्ड एज रिवॉर्ड असाइनमेंट। ये सबको सेम रिवॉर्ड, कुछ लोग ऐसे ही ग्रुप में नहीं बना लिया प्रोजेक्ट तो सबको ग्रेड मिल गया, बेकार बना दिया, सब चले गए। तुम्हें 2 बच्चों ने तो अच्छा काम भी किया था। तो रिवॉर्ड क्रेडिट असाइनमेंट, सॉरी दिस कॉल्ड क्रेडिट असाइनमेंट। क्रेडिट असाइनमेंट की कोई जिम्मेदारी नहीं ले रहा है, पूरे को सेम दे दे रहा है। गलत है ये। क्या करें वो हम अगले स्टेप्स में देखेंगे कि क्या करें। बट दिस इज योर वनीला प्लेन रीएनफोर्स एल्गोरिथम। कोई क्वेश्चन हो तो पूछ लो।
Yes, sir, I have two questions. Starting, sir, we were calculating probability of tau given theta. So, is it same as likelihood?
नहीं, लाइक्लीहुड ये नहीं है। लाइक्लीहुड ऑफ दैट प्रोबेबिलिटी ऑफ दैट टाउ है, इस थीटा के करस्पॉन्डिंग उसे चुनने का। हाँ
No, sir, what one trajectory
हाँ
calculating the probability of that trajectory is same as the likelihood.
likelihood of that trajectory with respect to this theta.
Yes.
हाँ हाँ
So that's why we were calculating in the product form.
वो तो प्रोडक्ट की फॉर्म में आएगी क्योंकि आपको लगातार मल्टीप्लाई करते जाना है ना। बिकॉज देखो दैट्स इफ यू टेक दिस देन यू टेक दिस देन यू टेक दिस, तीनों स्टेप्स की प्रोबेबिलिटी बना के ज्वाइंट प्रोबेबिलिटी निकालूंगा तो मल्टीप्लाई होगा।
Yes, sir. But sir, it may happen that okay, so in the starting, we assume that we are independent of, I mean, last state.
लास्ट हाँ
Last we
हाँ
were independent. There's a, I mean, assumption very important.
हाँ
Okay, so that's why we are doing multiplication.
मल्टीप्लीकेशन। हाँ तो वरना और भी ज्यादा कॉम्प्लेक्स फॉर्मूला बन सकता था। ठीक है, और किसी को कोई क्वेश्चन? दीपाली
Sir,
सोमा, हाँ दीपाली पूछिए।
sir, I wanted to ask if you will upload the lectures and the slides because I couldn't attend last few lectures and इसलिए
लास्ट फ्यू लेक्चर्स अब क्या होगा?
yes sir क्योंकि वो I was traveling and अब I'm back in India by the way so इसलिए
आप
attend
इंडिया आ गई हैं, आप तो क्वारंटीन में हैं, ये कोई और लड़की है।
नहीं सर I'm in India but I'm at home अभी कैंपस पे अभी आऊंगी थोड़े दिनों में।
गीतांजलि से कह रहा हूँ आपसे ये अपलोड कराएगी इसको एक एक करके। बट एनीवेज वी हैव शेयर्ड फ्यू स्लाइड्स, पता नहीं क्या उसमें सारा कुछ दिया हुआ है। मेरे लेक्चर वहां पे ही है, मैं उसी का सबसेट पढ़ा रहा हूँ, कोई नई चीज नहीं पढ़ा रहा हूँ।
जो सर आपने प्लेलिस्ट करी है शेयर वो
हाँ उसमें सब कुछ है, वो ग्रीन
हाँ।
ग्रीन करके बैकग्राउंड है उसमें शुरू में।
ठीक है बट सर वो फॉलो करने के लिए लेक्चर की कहाँ तक क्या क्या पढ़ा है उसके लिए चाहिए होता है कि इस लेक्चर में यहाँ तक पढ़ा क्या पढ़ा, तो इफ
तो आप
पॉसिबल
मुझसे क्या चाहती है वो बताइए।
अगर मुझे ये पता चल सके कि किस टॉपिक तक हो गया, या फिर मैं फिर खुद देख लूंगी कौन कौन से टॉपिक्स कवर हुए हैं, मतलब।
चलो इसको अभी कराते हैं। हाँ ठीक है, इसको कराते हैं। और किसी को कुछ
Thank
कहना
you.
है? हाँ
Instead of calculating gradient directly, we are taking log. So it will affect the gradient of j theta, obviously. So then what?
नहीं बट मोनोटोनिक वाला फंडा तुमने तो बताया, तो वो नीचे जाएगा बढ़ेगा तो ये भी ऊपर जाएगा।
So then we will normalizing.
हाँ नॉर्मलाइजिंग नहीं कहूंगा, मतलब अगर वो नहीं करते देन यू कैन नॉट डू दैट बिकॉज वो टी को हटा नहीं पाते, समझे? तो अब पूरे पे लेके काम करोगे तो दैट इज व्हाई वी डू सर्टेन थिंग्स। सेवरल टाइम्स आई वांटेड टू मैक्सिमाइज दिस और मिनिमाइज दिस, लेकिन मैं इसको नहीं मैक्सिमाइज कर पा रहा, तो मैं इधर आ गया। मैंने कहा इसको करता हूँ, फिर मैं कहा इसको भी नहीं कर पा रहा क्योंकि इसमें ये पंगा, फिर मैं इधर आ गया, फिर मैं इधर आ गया। इंटीग्रेशन करते थे ना पहले, वो सब्स्टिट्यूट करता जाता था। But we just have to show that both of these things are equivalent. If I minimize this, that will also be minimized. Sometimes it may happen I want to minimize this, but I am maximizing this. इसका maximization उसका minimization है।
If update will happen,
हाँ।
it will make the problem.
Update will happen क्या?
I mean, if we update theta in each equation,
हाँ।
so then we are taking the gradient of the.
बहुत सही क्वेश्चन पूछा ना तुमने, इसीलिए तो इसका अगला पॉइंट था कि इसमें पुराना एक्सपीरियंस रिप्ले नहीं चलेगा, तो वो अभी आगे आएंगे। तो दैट इज आई उसको क्या नाम दिया था हम लोगों ने, एक्सपीरियंस रिप्ले। सो दैट वाज कॉल्ड एज द, नहीं हाँ, रिप्ले बफर को वी नीड टू ये स्क्वैश एंड जनरेट न्यू रिप्ले बफर। वी विल टॉक अबाउट दिस, ये सभी कंफ्यूज हो जाएंगे, क्वेश्चन ये अभी समझे नहीं है। तो वेट, अभी आपको अपने आप वो क्वेश्चन समझ में आएगा जब मैं कल आपको फिर से एक बार दिखाऊंगा। बट दैट्स ट्रू। हाँ ठीक है, ओके, थैंक यू।